Okay, now I would like to explain about series leading connection and series opposing connection. So first one, series leading connection. Okay, here two inductors having inductances L1 and L2 are connected in series connection. So the current flowing through these two inductors is same. It equals to I. So this is the first end of first inductor, and it is second end of first inductor, and it is first end of second inductor, second end of second inductor. So here both inductors currents entering at first end. Okay, here at dot the current entering into the inductor. Here current entering into the inductor, and in second inductor from this point current entering into inductor. So this connection is called series aiding connection. So let us consider two inductors L1 and L2 which are connected in such a way that flux produced by the two windings is aiding. So whenever the AC voltage applied to the circuit, current I starts flowing in a circuit and the voltage is induced across the inductors, the induced EMF is equals to E1 and E2. So E1 voltage across the inductor, E2 voltage across the second inductor. First inductor voltage E1, second inductor voltage E2. Okay, now apply KVL to the circuit. Okay, we know that the KVL statement, sum of the voltages around the loop equals to 0. Here applied voltage V, first inductor across voltage E1, second inductor across voltage equals to E2. So KVL equation V minus E1 minus E2 equals to 0, or V equals to E1 plus E2. Okay, this is KVL equation for the above circuit. So next one, the induced EMF in first inductor. So the induced EMF equals to self-induced EMF plus mutual induced EMF. If only one inductor present, then only self-induced EMF is present. Here two inductors are there and which are placed very nearer to each other. So in each inductor, here self-induced EMF and mutual induced EMF are induced. So first inductor induced EMF equals to self-induced EMF plus mutual induced EMF. So similarly second inductor EMF equals to second inductor or second coil self-induced EMF plus mutual induced EMF. So first coil induced EMF E1 equals to, so first coil induced EMF L into di by dt. So here two inductors connection series connection. So the current in two inductors are same. It equals to I. So E1 equals to L into di by dt plus M into di by dt. So first term indicates the self-induced EMF, second term indicates the mutual induced EMF. So similarly second inductor induced EMF E2 equals to self-induced EMF L2 into di by dt, mutual induced EMF M into di by dt. Okay, let equation number 1 and it is equation number 2. So KVL equation V equals to E1 plus E2. So now substitute E1 E2 in equation 3, we get V equals to L1 into di by dt plus M into di by dt plus L2 into di by dt plus M into di by dt, or V equals to L1 plus L2 plus 2M into di by dt. So this is the equivalent circuit. So from this circuit we can write V equals to L equivalent into di by dt. So by equating these two equations we get L into di by dt equals to L1 plus L2 plus 2M into di by dt. Both sides di by dt cancel. So finally the equivalent inductance equals to L1 plus L2 plus 2M. In series aiding connection, the equivalent inductance equals to L1 plus L2 plus 2M. So next one, series opposing connection. Okay, here at dot marks the currents entering into the coil. So here see in first inductor here dot mark is there. So in first inductor from second end current entering into the coil. So next in second inductor here dot mark is there. So from first end the current entering into the coil. So this connection is called series opposing connection. In previous case, in first inductor current entering from first end. Similarly in second inductor also current entering from first end only. Here in first inductor current entering from second end, in second inductor the current entering from first end. So this connection is called series opposing connection. Here also the current flowing through the two inductors same. So let us consider two inductors L1 and L2 which are connected in such a way that the flux produced by the two windings is opposing. So if currents are flowing in the directions, then the flux produced by the two inductors are in opposite direction. Finally the resultant flux will decreases. So whenever AC voltage applied to the circuit, the current starts flowing in a circuit. So where E1 and E2 are voltage across the L1 and L2 respectively. So now by applying KVL, we can write V equals to E1 plus E2. So here E1 first coil induced EMF, E2 second coil induced EMF. So coil induced EMF equals to self-induced EMF plus mutual induced EMF. So here because of the current directions, the flux produced by the two inductors are in opposite direction. So the self-induced EMF and mutual induced EMFs also in opposite direction. So E1 equals to first one self-induced EMF L1 into dI by dt, mutual induced EMF minus M into dI by dt. So this mutual induced EMF due to second coil flux. Self-induced EMF is due to first coil flux. So first coil induced EMF E1 equals to self-induced EMF L1 into dI by dt minus M into dI by dt. So similarly second coil induced EMF E2 equals to second coil induced EMF L2 into dI by dt minus M into dI by dt. This is second coil mutual induced EMF. This induced EMF is due to first coil flux. Here minus M into dI by dt is first coil mutual induced EMF. So this EMF is produced by the second coil flux. Here two inductors are connected in such a way that these two inductors produces the magnetic flux in opposite direction. If magnetic fluxes are opposite, then automatically the EMFs induced also in opposite direction. So that's why here induced EMF equals to self-induced EMF minus mutual induced EMF. Okay, equation 4, 5, 6. So now substitute E1, E2 in equation 4. So equation 4 V equals to E1 plus E2. So V equals to L1 into dI by dt minus M into dI by dt plus L2 into dI by dt minus M into dI by dt. So this is the equivalent circuit. So from the circuit we can write V equals to L equivalent into dI by dt. So by comparing these two equations, can write L equivalent into dI by dt equals to L1 plus L2 minus 2M into dI by dt. So both sides dI by dt cancel. So finally L equivalent equals to L1 plus L2 minus 2M henries. So this is the equivalent inductance in case of series opposing connection. In series leading connection, the equivalent inductance equals to L1 plus L2 plus 2M. Here plus 2M in series leading connection and here minus 2M in series opposing connection. So in series leading connection, the equivalent inductance value high compared to series opposing connection. Okay, in parallel leading connection, already we derived. In parallel leading connection, the equivalent inductance equals to L1 into L2 minus M square by L1 plus L2 minus 2M. In parallel opposing connection, equivalent inductance value L1 into L2 minus M square by L1 plus L2 plus 2M. Numerators are same. In denominator, here plus 2M is there in parallel opposing connection, minus 2M is there in parallel leading connection. So similarly, in case of series leading connection, the equivalent inductance equals to L1 plus L2 plus 2M. In opposing connection, L1 plus L2 minus 2M. Okay, first this is series leading connection. This is also series leading connection. Here currents entering in both inductors from second end. Here current enters in both inductors from first end. So here in first inductor current entering from first end, in second inductor current entering from second end. So here also, so in first inductor current entering from second end, in second inductor the current entering from first end. So these two circuits are series leading connection and these two connections are series opposing connection. So series leading connection equivalent inductance formula, series opposing connection equivalent inductance formula. Okay, finally we can say that in series leading connection, in parallel leading connection, the equivalent inductance values are high, so compared to series opposing connection and parallel opposing connection. In leading connection, the equivalent inductance is more compared to opposing connection.